Hi, so in this lecture we will go little deeper in electrostatics. In the last lecture we have seen that for a parallel plate capacitor the energy stored was half CV square, right. Now we go to the like little more description on this, right. So there you can see that these are let us say two parallel plate capacitor, and let us say the area is equals to A, okay, and then I am applying potential V, and and I am applying potential V, and then this is the side view or the cross sectional view, and see this is the electric fields, okay, and so let us say plus Q charge is at the top plate and minus Q charge is at the bottom plate. So according to potential is V, so according to the formula we know that C or the capacitance is equal to epsilon A by D. Now what is this epsilon? This epsilon is actually epsilon naught into epsilon R, A into D, A by D, okay, and this is dielectric constant, right, the relative permittivity, right, epsilon R, and for if it was like just the vacuum or the air, then we would have written only the epsilon naught, and then we know that energy is equals to half of C into V square. Now we know that what is force? Force is actually dF, if the work done is W, then dW dr, or the energy, first derivative of energy with respect to the distance or the displacement, okay. So the electrostatic force between these two plates will be this is F normal, that means the normal force, this electric force, okay, this is the electric field direction, and also this, let us say this is the electric force direction also, okay, the normal direction from one plate to the another is equals to W by D, and what is W? W is the energy stored, so that is half of C V square divided by D, okay. Now what is C? N equals to half of C is equal to epsilon naught epsilon R A by D, so this will become D square and on top V square, okay. Now one important point to note here is, see this epsilon naught is very small, almost 10 to the power minus 8 or in that order, in the minus 8 to minus 12 order in different like unit system. Now this force is usually, that is why this force is very small, because D in macro scale D is also large. Let us see if it is like 1 centimeter or so, and then area and voltage everything is in that level, then everything is in that scale, then because of the epsilon naught this is very like the normal force is very small, like the electrostatic force between these two plates. But as we do miniaturization, then this D can become smaller and smaller. So if we have two plates in separation of, let us say, few nanometers, then in that case I am getting a 10 to the power minus 9 at the bottom, okay. That 10 to the power minus 9 takes care of that epsilon naught, and because of that the force can be actually very high. So we will see that with some example later on. So now this is the normal force. Let us go to the next case, and next case is like what is the transverse force. So let us say I have two plates like this. So the here these two plates are of exactly same geometry, means both are having the same breadth, length, width, thickness, etc., and they are separated by some gap d. The difference from the last case is now they are not exactly on each other. They have a overlapping area of x, that is the bottom plate. Let us say both the plates were at the same place initially, then the bottom place is moved away little bit. So it is something like this. So this is the top plate and this is the bottom plate, and then I am moving the bottom plate. So you can see it's like this. So the overlapping area where this is these two plates can form a parallel plate capacitor is small, and it's smaller than its actual area, and that is b into x, right, b into x. Okay, fix the axis. Let's fix the axis system also. So this is x, this is y. Now the capacitance is equals to C is equals to B x epsilon naught divided by D. Capacitance between these two plates is Bx epsilon r epsilon naught divided by D. Now Q equals to C into V, and W is equals to half of C V square, right, and a tangential force, because or the force in the x direction, so that is the direction of movement also. So tangential force F transverse, or the transverse direction force F transverse, is equals to delta W by delta x. Let's write it as del x into half of CV square. So what is half CV square? Half of B x epsilon r epsilon naught divided by D into V square, right. Okay. So if we do del x, then we get B of two D to B of epsilon r epsilon naught into V square. So now here you notice that the displacement is x, right. So as I am moving the plate, my transverse force is generated, but it is independent of the movement, because transverse force, whatever be the displacement, the transverse force ultimately is a constant with respect to x. So the transverse force is same wherever how much is the value of x irrespective of that. So let us write down both the normal force and transverse force again. Okay. So we got that normal force Fn is equals to half of epsilon naught epsilon r bx by d square, and at the top it is v square, and transverse force is equals to half of b into epsilon naught epsilon naught epsilon r, then below it is d into v square. Okay. Okay. Now first of all you can see that the normal force is dependent on the distance between the plate, right, that is distance between the plate, that is d square. So, as we move the plate normally, or like in vertical direction, the force changes, right, because the d will change, but the transverse force is because of the horizontal movement of the plate, right, but this is not changing with respect to the displacement of the plate. Okay. So, this is one point to note, and from these two equation, let us say we call it 1 and 2, if we divide 1 by 2, then we can get that if n by f transverse is equals to x by d, right, x by d. Now, in this usually what we are, x is the displacement, right, how much is we are shifting one plate from another. So, usually for microscale systems, x are very greater than d. Okay. X are very greater than d, because the gap between two plates we keep it very small. So, in that case we can write that if n is very greater than Ft, or the normal force is much higher than the transverse force. And one point to note here is this x, or the lateral movement, is actually we control by like our design, how we are making the device and how we are going to move it, etc. But the transverse force, while the gap between the two plates is gap between two layers. So, it is, or there are some microfabrication or fabrication constants, because of that we cannot make it very high. Okay. We cannot make it sometimes very high, it will be a micrometer, or in like 1 micrometer, or even few nanometers, or like in nanometer scale, okay, few hundreds of nanometer, etc. So, usually the d, which is our gap between two plates, or actually gap between two layers as such of our device, is very small. Now, once we know some basics of electrostatics, we will try to couple the electrostatic force with the mechanical force, what we learnt in our previous modules. Okay. So, I am first drawing two different cases. So, this is a fixed plate, let us say this, call this A and B. So, A is a plate which can move, okay, and this is supported by two beams which are connected in the opposite direction by some fixed support, as it is shown by this shaded area, and this B plate is already fixed at the bottom. Okay. At present there is no electrostatic force, these are not electrically connected, so there is no force, and the beam is like the plate A is its original position, and let us say the gap between them is d, between these two plates is d. Okay. Now, what we do, we connect electric potential to this. So, let us see what happens. So, these are the supports, and the bottom plate anyway will not move because it is fixed, it cannot move, but the top plate will come down because of electrostatic attraction. So, this is just because of the drawing it became like that, but no beam actually bends like this. So, anyway, the point is that the bottom that the top plate now come down or become even more closer to the So, initially let us say it was here and then it comes down by some distance y. So, now this gap which was earlier d, it becomes d minus y, right. So, now some electric potential is connected. Some electric potential is connected. Okay. So, these two are the fixed support, this one and this one are the fixed support, and this is a fixed plate which is electrically connected to the ground, and the top plate is connected to some positive potential. Okay. Now, these are there will be electrostatic attraction, and because of that the top plate A comes even closer to B. Now, at this condition, like while it is bent, what is the electrostatic force acting on that? Electrostatic force let us call it Fk is equal to minus of Ky. So, we need to put direction in one side it should be positive and another side it should be negative. See, this y is the deflection, right, and we know that force is equal to k into x, where k is the stiffness constant. So, let us assume that this plate A, whatever it is, whichever beam it is connected to, the effective stiffness constant is finally k. So, the force is acting upward, and that is minus Ky. Sorry, I wrote wrong here, it is not electrostatic, it is elastic force, that is the mechanical force, right. So, it is elastic force. Now, we will see what is the electrostatic force. So, electrostatic force, and as we already have seen that is our normal force, right, because here both the plates are exactly on each other and there is no transverse movement or horizontal movement, only the vertical movement. So, the force is W by D, right. So, electrostatic force is Fe equals to W by D is equals to half CV square divided by D minus Y, because the gap is now actually not D, it is D minus Y, right, and C is also can be C also can be written as epsilon r epsilon naught A divided by C is now also epsilon A by D, that is D minus Y. So, D minus Y comes from the capacitance also, so it becomes D minus Y whole square into V square, right. Now, this force, that is the, so electrostatic force is acting downward, it is pulling this A plate, right, whereas the stiffness or the elastic force is pulling it upward. So, at equilibrium, both the force will be same. So, force is equal to elastic force, electrostatic force is equals to electric force, and that gives us half of epsilon naught epsilon r A divided by d minus y whole square v square is equals to ky. So, from force balance we get that half in some constant into v square divided by d minus y whole square is equals to ky. Now, if we take this d minus y whole square on the other side, then we get a cubic equation of y, that is y cube term will be there, and by doing solution, or you can solve it by the usual mathematical techniques, and then you will get 3 roots, because this is a cubic equation, and from that equation you can find that which root is which root we can neglect or which is not possible imaginary root, and one will be like a proper root, and accordingly we can get that what is the distance. But to understand this phenomena more critically, we need to understand it the graphical, we need to understand this solution from graphical technique. Okay. So, that is what we are going to do next. So, what I am going to do, I am going to draw force versus displacement for both the cases, means elastic force as well as for the electrostatic force, and with respect to the gap between the two plates. So, I am just normalizing the force F by kd, where d is the initial displacement, and then we have in the x axis y by d, right. So, as it is y by d, the maximum can be y can be d. So, it is 0 to 1, the maximum possible range is 0 to 1, right, because maximum possible range is that y can go maximum up to d. So, y by d maximum possible value is 1, right, and we will see how the force goes, right. Now, you see from our expression that elastic force is equals to k into y. So, elastic force is directly related to the displacement by linear relation. So, we can draw this is the elastic force. Okay, this is the elastic force, and it will go through 0 0, because at y equal to 0, f equal to 0. See, elastic force is equal to f is equal to minus ky. So, at y equal to 0, f equal to 0, and this is directly related. Now, what is electrostatic force? Electrostatic force is half into divided by like some constant divided by d minus y whole square. Now, d minus y whole square, this is like a parabola equation, right. Y square is equal to 4ax, y square is equal to 4ax, where you have a like one side y is having square, and another side you have power 1, and the other side you have power 2. So, it is like y has a quadratic power, whereas force is only unity power, right. So, this is parabolic equation, and at y equal to 0, electrostatic force have some value. It is not 0 like elastic force, it has some value, right. So, and it is its like minimum value. As the y goes down, the electrostatic force will increase more. So, it will go something like this. Okay. Now, so this dotted line is my electrostatic force, and the continuous straight line is my elastic force, and there is a solution at this point, right. There is a solution at this point, and let us call it point A, and there is another solution at B point, right, where the elastic force and electrostatic force are same. Now the interesting point you should note is, as initially the gap is D, right, and there is no deflection, so y equal to 0, so the elastic force is 0. Initially the gap is 0, so the gap is D, so the deflection or the displacement of the top plate is 0, so the elastic force is 0, but there is certain value for electrostatic force, and that will start pulling in the top plate or A plate. Now as it increases, I mean the it is pulled down, or the top plate is pulled down, the elastic force increases because deflection is increasing, right. So F is equal to Ky and the deflection is increasing, so the elastic force is increasing. So at some point this elastic force becomes equal to the electrostatic force, right, electrostatic. So this is one of the solution. But the point to note here is that this is a stable solution. Why? Because you see that if it increase little bit more, or if we have a perturbation from this A point little bit on the other side, or at this side or on the right hand side, then the elastic force is still higher than the electrostatic force. So the elastic force is still higher than the electrostatic force. So it will be able to pull it back, I mean the elastic force will be able to pull the top plate to its original position, right, or pull it back to the A position, solution to the A position. But as it moves more and more, or as it goes down more and more, the top plate, then it reaches another point, which is another solution, that is the B solution, B point. But in this point, if you note that the elastic force and the electrostatic force are same at this point, right. But the interesting point is here, now if it increases, if because of some perturbation the top plate goes down even little more, then what happens is, then the electrostatic force is more than the electrostatic force is more than the elastic force, right. And in that case what will happen, this will the top plate will get more and more pulled in towards the bottom plate. So this is called pull-in phenomena. This is called pull-in phenomena, where the top plate will snap onto the bottom plate, okay, because elastic force or the mechanical force is not able to pull the top plate back to its place, because you see the mechanical for the mechanical force, the force is increasing with F is equal to Ky, that is linear, but the electrostatic force is increasing with power of 2. So it is more and more it increases, and then at some point while it is very close, the D becomes 0. So the theoretically or technically the electric force becomes almost infinite, right. So it will not be able to, like the mechanical force will not be able to pull it back, right. So what we can tell from here, that the solution A is stable solution. Let us call this solution XA, and let us call this solution a, sorry, this is this axis we have considered y, so we will write y. So let us call this ya and this is yb. So solution A, that is our xa, is stable solution, and sorry again so solution A, ya is a stable solution, and for y less than ya or y greater than ya, but y less than yb, top plate will come back to A position, okay, and solution will merge to ya, right. If y is greater than yb, then the top plate will be pulled in on the bottom plate, or it will snap on the bottom plate, and this is called pull in. This is called pull in, okay. Solution at B point, that is yb, is an unstable solution. Now one important point is that, okay, A solution is the stable solution and B solution is unstable, but while it starts moving, it will first cross A, right, because initially y equal to 0, and then as it gets pulled down, then it will go from 0 to towards 1, like y by d if I take, right. So it will first cross A point, and then there is no reason for the plate to go to the B point. Now what happens if we increase the electric potential? So that you can mathematically see that as we increase the electric potential, this curve will move more and more upward. Because the constant will increase, right, and you will get something like this. So the nature of the curve will be same, but it will move upward, right. And these 2 points, so now the intersection is at this point, A intersection, and B point is at this, and at some point it will come at for some potential where there will be a single touch between the mechanical force and the electrostatic force, let us say something like this. And this voltage where we get just the elastic force and electrostatic force is matching only at a single point, this is called pull-in voltage or Vp, because above that voltage, any voltage, there is no point where the mechanical force is higher than elastic force, right, higher than the electrostatic force, because on above the pull-in voltage, see the electrostatic force will go like this. So at all the for all the all the y's, it is already above the mechanical force. So it cannot be like mechanical force will not be able to pull in to restrict the pull in, but if it is only below this point Vp, then only it will be able to only will be able to pull it back to its original space or original place, that is upward. So then if it is only below this pull-in voltage, then only these beams will be able to pull it back to its original space or even to the let us say the another solution, which was the stable solution A point, right. Otherwise it will snap on the bottom plate. So this voltage Vp is called pull-in voltage. And the mathematical derivation about this we will do in the next class.